Ansari, and today is day 66 of my project. So what I'm doing is I have some histopathology images of cerebral aneurysm, and I'm building a pipeline to quantify the amount of ingrown tissue in that sac. So what you have to do is you can upload an image, and the pipeline will give you the area of the ingrown tissue in that image. Not only that, you can also upload an image with a folder with a bunch of images, and it will give you the area for all of them. So you don't have to do one by one. So before I talk about in detail how I did it, I want to give a little bit of background about myself and the project itself. How can I? Oh, okay. So I'm originally from Nepal. It's a small country between India and China, and it's famous for the tallest mountain in the world. If you are wondering whether I have climbed this mountain, the answer is no, but I hope to climb one day. I did my schooling from Nepal. However, for my college, I decided to come to United States. In 2021, I joined Caldwell University in New Jersey. I'm studying a biology and computer science here. And last summer, I did a research wet lab at Rutgers University, where I studied neurology. And then this summer, I'm thankful to HuBMAP and Dr. Sadar's lab for providing me this opportunity to work at University of Florida and learn about machine learning in image analysis. Before I started this project, I had no idea about any of these tools and libraries. I didn't know anything about PyTorch, TensorFlow, OpenCV. However, this program has been an invaluable learning experience. The guidance and support from my mentors and the resources available through the program helped me learn and apply deep learning techniques, which I had never done before. This experience has significantly enriched my skills and understandings, and I'm very deeply thankful for this chance to grow through this program and internship. So, coming back to my project, I'm using a unit-based pipeline for quantifying the amount of ingrown tissue from the histopathological images of cerebral aneurysm. UNET is a convolutional neural network. So when I say convolutional, what it means, there is a filter of certain size, and it scans over all the pixels in the image as shown in the image here, and generates a number. And this process goes for multiple layers until it makes a prediction. And this is inspired by the human brain, where the neurons are interconnected to each other. In similar fashion, in the convolutional neural network, there are multiple layers with multiple nodes, and they are connected to each other. And pipeline in machine learning means it's an end-to-end construct uh, that consists of multiple machine learning, one or multiple machine learning models. So for example, in this flowchart, the red rectangle is uh, represents a pipeline, and the arrow can be a model or some other post-processing steps or any kind of steps. So the whole rectangle represents a pipeline, and each arrow is a machine learning model or some other steps. And histopathological images, here is one example of histopathology image from cerebral aneurysm. Cerebral aneurysm is a weak and thin spot in the blood vessels that balloons out, and it bursts under high blood pressure, high high pressure of the blood flow. And this bursting can lead to serious conditions such as hemorrhagic stroke, brain damage, coma, and even death. About 6.8 million people in the United States, which is 1 in 50 people, have unruptured brain aneurysm. and this research can prevent them from rupturing. Current treatments include drilling through the brain and using a tiny metal a clip to pinch that opening to seal off the blood flow. And the second method is endovascular coiling, where they insert a catheter from the groin region and fill the sac with coils to stop the blood flow into the, and it prevents the sac from rupturing. Surgically, surgically, the problem with these two treatments is that there is a chance of high reoccurrence and it has to be retreated. And the surgically harvested and autopsy-derived specimens of human brain aneurysm shows that durable cure is achieved by intra-aneurysmal wound healing. So our collaborator lab is trying to induce intra-aneurysmal wound healing through tissue ingrowth. And our lab needs to quantify the amount of ingrown tissue. So the problem for us is to quantify the amount of tissue inside the sac from the histopathology images. And the solution includes finding the area of the ingrown tissue divided by the total area of the sac and multiply with 100 to get the percentage. First step would be to identify the boundary. And then once we identify the boundary, we can get rid of the outside area and then get only the tissue region. Then we can also get the area of the sac region and then calculate the percentage. Looking each step in binary image form, all we have to do is count the number of white pixels in this image, tissue region mask, and then we have to count the white pixels in the sac zone mask, and then we can simply use the formula to calculate the area. So what's the challenge here? It's finding the boundary. So to find the boundary, we used a unit-based pipeline to predict the boundary. And then we can also use, once we predict the boundary, we can use some post-processing techniques to get the sac zone and then do a scalar product to get the ingrown tissue area. So how does the unit model work? You have to give an image and ground truth of the boundary, and then it goes through layers of training and does a prediction. And then it compares the predicted boundary with the ground truth and computes loss, and then comes back, updates, improves its parameters, and goes through another set of training and then make another prediction. So it keeps on doing this improvement unless the machine gets the best it can. So we had total of 64 images. So 40 of them I used for training, and 12 for validation, and 12 for testing. And since 40 is a very small number for training, I use some augmentation techniques shown here in the images and to increase my data set. And then I used 200. I used these 5 techniques, which led us to a total of 200 images for the training. These are some of the sample of my images and the respective ground truth that I used for my training. And this is the predictions made by the machine. The middle ones are the original prediction, and on the right ones are the predictions that were thresholded using 0.5 thresholding. 0.5 thresholding means all the pixels values less than 0.5 will become 0, and the ones equal or more than 0.5 will become 1. And these are the overlay image of the ground truth and then the predicted mass on top of the original image. We wanted to see how accurately and precisely these boundaries are predicted by overlaying on top of the image. So looking at the image, it looks pretty good. However, we also use some of the metrics to measure the performance of our model. We used accuracy, recall, precision, and Jacquard and F1 score. Accuracy basically represents out of all the black and white pixels in my actual image, how many of them are predicted correctly in my predicted mask. Recall is out of all the white pixels in the actual, how many of them are predicted correctly. And the precision refers to out of all the white pixels in my predicted, how many of them are the actual in right spot. And then Jacquard is out of all the white pixels between these two images, sum of the total white pixels between actual and predicted, how many of them are common. And F1 score is the harmonic mean, which is given by this formula. So those matrices that I showed, the accuracy of 0.9629, Jacquard of 0.19, recall 0.26, and precision 4. These were all for 0.5 thresholding. So I proposed rather than using a manual thresholding of 0.5, what if I try other thresholdings, such as Lee thresholding? What if I plot ROC curve and use Uden index and distance to 0, 1 to find out optimal thresholding? So, so in ROC curve, I plotted the ROC curve. In ROC curve, on the y-axis, we have true positives, and on the x-axis, we have false. So we want a number that is higher on the y-axis because we want true values, and then low on the x-axis, which is towards the top left corner. So if we have a graph like this shown on the bottom right corner, we can easily say that this point, this threshold is better than this, and this threshold is better than this. However, for a continuous curve, it can be a little tricky. So we used the Uden index to find the optimal threshold in this continuous curve, as well as distance index. And we can see the Uden says the optimal threshold is 0.15, and the distance index says the optimal is 0.17, which are pretty close to each other. And these are the formulas that I used for finding those optimal indexes, in optimal thresholds. And these are the result of my total average result of my 12 predictions. And we saw that 0.5 thresholding gave us the highest accuracy and precision. And the Lee thresholding gave us the highest F1 value and the recall. And Uden thresholding gave us highest Jacquard score. So the choice of thresholding depends on the requirement of the project. But for our project, I wanted the white pixels in my predicted mask to be the white pixels that makes the boundary, which is given by the Jacquard values. But we also have a lot of noise and still a higher Jacquard score. So I also need to consider the precision. Therefore, the better thresholding would be the one with higher Jacquard and higher precision. These are some of the areas predicted by the model, given that we have a complete boundary. So, and the to-dos are to fine-tune the model to predict a complete boundary rather than broken segments. And then second can be apply a optimal post-processing techniques to complete the broken boundaries. And then we are also proposing to use a incongruent tissue as mask directly and predict the incongruent tissue by eliminating these post-processing steps. If we can do that, the errors will be reduced and the model will be more robust and reliable. And I did a simple trial on using the incongruent tissue as my binary mask. And these are the predictions, which are very close to what we need. However, I believe that if we use larger data sets, we'll get more accurate result because we worked on only 40 images, which is a very small number for training a model. And finally, I would like to thank Dr. Sadar, who is my PI, and Dr. Ho, he provided us with the data, and my direct mentor, Dr. Ahmed, and my whole lab who helped me through this process. Thank you.